let's talk about how we can solve electric circuits. A couple of examples from the last video. So let's begin by taking an example of a series circuit. And in this circuit, we will have a voltage source, is probably the way I should say it, voltage source, and we will have 3 loads of some sort, which I'll represent with these resistor symbols here. Okay. Now I'll give you some information about the 3 loads that we have. We'll have a voltage for load number 1, a current, and a resistance. And the only number I'm going to tell you is that it's a 2 ohm resistance. And then for voltage number 2 and current number 2, I'll leave those blank as well. And we'll have a resistance of the second load of 4 ohms. And then down below here, I'll write the voltage of load number 3, the current for load number 3, and the resistance for load number 3. And let's make that let's make it 3 ohms. And we can also describe the total voltage. I'll write these sort of on the side, supplied by this voltage source, and then that will produce a current total for the circuit, and it will produce, or we can calculate, a total resistance for the circuit. I'm going to tell you that this circuit has a voltage of 70 volts. And so when we say solve the circuit, what we mean is we have to somehow fill in all the missing pieces that are here. And we'll do that using Kirchhoff's laws for series circuit. All right. First thing we'll notice is it is a series circuit because all of the loads are on the same path. If everybody's on the same path, all the current must travel through every load, and therefore we can say that that is a series circuit. Now, we have 70 volts going through, or being supplied by this voltage source. However, that 70 volts is the total, and we also know that that 70 volts is kind of like the energy that's causing the electrons to move. And every time the energy or the electrons go through one of these loads, they lose some of their energy. So after they go through load number 1, they will miss or lose some of that voltage. And then through load number 2, and again load number 3. So all we know about voltage in a series circuit is that the voltage drop at 1 and at 2 and at 3 has to add up to 70. But that could be any 3 numbers that add to 70. So I can't really start there. I have no information about the current, but I do have information quite a bit about the resistances. So let's start there. Let's remember that in series, Kirchhoff's law says that the total resistance is equal to the sum of all the resistances in the circuit. Since I have 3, I'll just go as far as 3. And if I write them down, if you go back, you'll see that the first one, R1, was a 2, and then we have a 4 and a 3. So 2 ohms plus 4 ohms plus 3 ohms is the total resistance. And that's easy enough to do in our head. 4 and 2 is 6, so this is 9. Right? Oops, let's put that over here. Let's put RT equals 9 ohms. Now, I just realized that I was trying to make the math easy for you, so I'm going to make a small change. I guess my brain isn't quite on today. I'm going to change this little guy over here, this voltage. I'm going to change that to 90 volts because I wanted to make the math simple. So let's make that correction, and now let's continue. Okay, so we've found out what the total resistance is. Good. Now that means that this number that I've drawn right here, this 9 ohms, is the total resistance, and it can go here. So So now I know that this is 9 ohms. Now, remember, we also have, besides Kirchhoff's laws, we also have Ohm's law. And Ohm's law says that V equals IR. So if you look at what's happening near the power source, near the voltage source, we have the voltage, 9 volts, and the resistance. We should be able to figure out what number goes here where the I is using Ohm's law. So I'm going to call this first thing we did step 1. And over here I'm going to do step 2, which is to use Ohm's law, V equals IR. And because I'm talking about the total voltage, the total current, I'm going to put the little t's in here so I know which part of the circuit I'm talking about. And that means that 90 volts is equal to I total multiplied by 9 ohms. And so if we divide both sides of this equation by 9, 90 over 9 equals IT, I total. So that's going to be 10, right? So 10 amps is the current. So you have to remember the units for all these things and put them in at the end. The total current is 10 amps. So I can go and put that over here now, 10 amps. So I've finished off that whole part. I've solved all those things. Now, what's the next step? Well, the next step, if you look at the series circuit again, remember Kirchhoff's law for current. All of the current begins at the voltage source, and it must travel all through the circuit. It must all go through load 1. It must all go through load 2. Sorry, that's load 3 on load 2 and load 1. Doesn't matter the order. All of the current must go through, all of them, which means the currents are the same everywhere. So what I'm going to do is, for step 3, it's kind of an easy step. I'm going to write this, step 3. Maybe draw a line here. Step 3, the total current is equal to the current at load 1, which is equal to the current at load 2, which is equal to the current at load 3. And since the current that's total is equal to 10, that means all the other ones are also 10. 10 amps, 10 amps, and 10 amps. So that's an easy one. Current is the same. Now the next step is to do Ohm's law 3 times. You'll notice that at load number 1, I'm missing the V, but V equals IR, right? So I'll write it down here as step 4. Step 4 would be to do V1 equals I1 times R1, and V2, do the same thing at V2, and do the same thing at V3. Now, whoops, 3. Sorry. Now you can show your work here. It's a good idea to show your work. Oh, I did it again. All right, V3, I3, R3. But if you look at these, they're all very simple. In the first case, we have 10 amps times 2 right here. See those? So 10 times 2 is 20. So for this guy down here, this equals 10 times 2, which is 20 volts. Okay, and then for number 2, we have 10 times 4, which is 40 volts. And for the last one, we have 10 times 3, which is 30 volts. So 20, 40, and 30. We can go and put those numbers in, and lo and behold, we will be finished the circuit. 20 volts, 40 volts, and 30 volts. Now remember the other thing we can do as a double check. We can check that we're right because there's also a voltage law that says the total voltage is equal to the voltage drop at 1 plus the voltage drop at 2 plus the voltage drop at 3. And I just calculated them, 20, 40, and 30. But the total voltage was told to me at the start of the question to be 90. Here it is, right here. So my 3 voltages must add up to 90. And we can see that they do, because we have 20 and 40, which is 60, plus 30 is 90. So that kind of verifies that I did everything right, because this is true. 90 equals 20 plus 40 plus 30. So it works out that 90 equals 90. So I kind of know that my answer is correct. All right, so that's how you deal with a series circuit. You kind of plug away at it. It's like a puzzle. I did step 1, 2, 3, and 4, but sometimes step 4 might show up as step 2, and the steps can be out of order. So you have to kind of look at what you've got and try to figure it out as if you were solving a puzzle. You have all these things at your disposal as your tools, but the order you do them in might change. Okay? All right, let's have a look at how a parallel circuit might work. So let's draw a parallel circuit. And again, I'm sure you did these in grade 9, so this should be pretty much a review. Let's make 3 little resistors in parallel here. 3 little loads of some sort. We don't know what they are, but like bulbs and motors and other things. Okay. And again, I will write in here, let's write it all in black. The voltage of 1, the current of 1, and the resistance of load number 1. But all I'm going to tell you is this is going to be 2 ohms. And we have a voltage at load number 2, a current at load number 2, and a resistance at load number 2. But I'm not going to tell you anything other than this is 4 ohms. And then we have a voltage at load number 3, a current at load number 3, and a resistance at load number 3. And I'll tell you that this resistance is going to be 8 ohms. All right. And then over here at the voltage source, I'm going to say V total and I total and R total. This time though, instead of giving you the V total, I'm going to give you the I total, which is 10 amps. Okay. So when we look at this, we remember Kirchhoff's laws. We know that the voltage will be the same across every load. But I have no numbers for voltage, so that won't help me. We know that the current of loads 1, 2, and 3 will add up to the total. So we know they'll add to 10, but we don't know which numbers to put in for which one. There's lots of different ways you can add up to 10. And you don't just divide it by 3, that wouldn't be right, because the resistances are all different, right? And remember, if you're a crowd going through here, more of the crowd is going to go through the least resistance. So you should expect a bigger current at load number 1 and the smallest current at load number 3. But the resistance, I have 3 numbers there, and I can start with that. Now remember, in parallel, doing resistance is a little bit tricky. It's a reciprocal relationship. 1 over the total equals 1 over R1 plus 1 over R2 plus 1 over R3. So that when you put your numbers in here, 1 over RT turns into 1 over 2 ohms for resistance 1, plus 1 over 4 ohms, plus 1 over 8 ohms. Now we have to add these fractions. And if you recall, adding fractions requires a common denominator. And so we can get a common denominator of 8 for these 3 fractions. I can turn the first fraction into a number with 8 on the bottom if I multiply it by 4. So if I multiply 4 by 2 to make an 8, I have to multiply the top by 4 as well. If I multiply this one, the second one I have to multiply it by 2 to make an 8, and I multiply the top by 2, and the last one I don't have to multiply anything, it's already an 8. So there's my common denominator, and that means that 1 over RT is equal to 4 plus 2, which is 6, plus 1 is 7 over 8. But that's not the answer. That's 1 over RT. In order to figure out RT, I have to take the reciprocal of both sides of this equation. I have to flip both sides upside down. RT flipped upside down, the 1 goes on the bottom. But remember how if we have a 1 on the bottom, we don't show it because dividing by 1 doesn't do anything. So you flip it upside down, you get the value of RT, then it would be 8 over 7. And if you take 8 and you divide it by 7, you get an answer of about 1.14-ish. Okay? And what we're going to do for simplicity is we're going to say that in our class we're going to always round off to 2 decimal places. 2 decimal places. Because the actual answer is 1.142857, you know what I mean. We'll round it off to 2 decimal places like that, 1.14. Okay, so if I go back to my picture, I can write that in, 1.14. So I'll write it in red, 1.14. And it would be ohms, right? We shouldn't forget to put the unit ohms. Now, what am I going to do? Well, that was my step 1, all of that work. Okay. My step 2, let's draw it over here while I have space, is going to be look at my totals again and figure out using Ohm's law what the voltage is. Vt equals It equals Rt. Because I know the I is 10 amps and I now know the R is 1.14. So the voltage then must be 10 times that, or 11.4 volts. So now I got that one, 11.4 volts. Perfect. Step 3, in this case, would be what I'm going to do next is realize that Kirchhoff, while I'm here, I'm going to put the ohms in there that we said we should have put. Kirchhoff's law for voltage tells me that the total voltage in a parallel circuit is equal to the voltage drop at 1, which is equal to the voltage drop at 2, which is they're all the same, basically. So that means that if I have 11.4 for the total, which I just figured out up here, then that means that all of these are also 11.14. They're all the same. So I don't even have to really write that down, do I? I can just know that they're all going to be the same, and I can put them all in here. Doesn't even require me to write anything down, really. And then we're going to do, guess what? 3 times we're going to do Ohm's law. Once for this guy, because we can figure out the I, because we have the other 2. Once for this guy, and once for that guy. So our last step will be to do 3 little Ohm's laws. I'll go down here underneath and do it. Our last step will be 3 Ohm's laws. V1 equals I1 R1. And then we're also going to do V2 equals I2 R2. And we're also going to do V3 equals I3 R3. In the first case, we have, let's go back up to number 1, just so we can make sure. We have 11.4 volts. Oh, I'm sorry. Yeah, 11.4 volts and 2 ohms. So I can put in here 11.4 volts. I don't know the I, but I know that it's 2 ohms. And so if we divide both sides of this equation by 2, we will get the answer. And if you divide 11.4 by 2, you can either use your calculator or you can do that in your head. It comes out to about 5.7 amps is current number 1. Now, let's go look at, we can go write that in and then we can look at voltage and resistance for number 2. So we said 5.7 here. Good. Now let's look at the second one. We have 11.4 and 4. So we'll go down here and we'll do the math for that one. 11.4 volts, I2, and 4 ohms. So this time I'm going to divide 11.4 divided by 4, right? 11.4 divided by 4 equals I2, and so 2.85 amps equals I2. Good, we got that one. 2.85. Let's go write that one in, and we'll get the other numbers. And we do the last one. Nice and simple. 2.85. Here we have 11.4 and 8 ohms now for load number 3. So we go down here, 11.4 equals I3 times 8. And we divide both sides of the equation by 8. And so I3 will be 11.4 divided by 8, which is really small, 1.43 if you round it off to 2 decimal places. Oops, and I should put in there that it's amps because this is current that I'm working on here. Amps. equals I3. So let's go put in 1.43. 1.43. Now, it looks like we're done. But we can also do a double check. We know that the current is added. So if I take this current right here, and I add it to this current, and I add it to that current, it should work out to a number that's going to be very close to 10. So let's see what happens as our check. If we add up those three numbers, let's go down here, down, down, down. Good. And let's look at it. We have Kirchhoff's law that says the total current should be the sum of the three currents. And we know that it's 10. And so we have an I1 of 5.7. And then we have 2.85. And we have 1.43. And so if you add those up, 5.7, 2.85, and 1.43, you get this number. 9.98. Now remember, we rounded off these numbers. And so even though that's not exactly, it's close enough because when we rounded off these numbers, we would have lost a little bit at the bottom end here of this number. So as long as you're super close, okay, you know that you're right. If you added that up and you got 8.4, that's not close enough. That would not work. Even if you got 9.5, that's not close enough. You should be able to get either 9.98 or possibly 10.01 or something very close to 10, very close to 10 because of the rounding. And that proves that we've done everything correctly. So that's how we do the parallel circuit. Now I'm just going to show you one other thing. If you're not very good with fractions, I want to go back here and take this little equation right here that we drew. And I'm going to stick it all together and move it down to the bottom. So just give me a second to do that. It's not letting me do that. All right, well, why don't we just copy that? Right, and I'll just put it down here and I'll paste it. So paste. There it is. All right, I'll grab it and I'll bring it down. And what I want to do is I want to show you an alternative way to work with this. Let's say you're not very good at fractions and you don't understand common denominator and you've tried it but you always get the wrong answer. You can use your calculator to help you figure this out. Just let me get down here where we can work on it. Okay, good. Well, because it's all 1 over, 1 over, 1 over, if you look on your calculator, there's a button you can press. There's a button on your calculator that either has 1 over x, or it might say this, x minus 1. Both of these buttons are the 1 over buttons. They mean the same thing. So what you can do, if you wanted to add up these three numbers without a common denominator, you can press the following things on your calculator. You can press the number 2, I'll put the buttons, right? And then, after that, press your 1 over x button, or x to the minus 1, depending on which calculator you have. Okay, I'll put it underneath. If you have the other calculator, another kind, it might say that. So that means you've just made it into 1 over 2. Then you can press your plus button, and you can press the number 4. And then you can press your 1 over x button, or x minus 1, whichever you have. That turns it into adding it as 1 over 4. Then you can press your plus button again, and then you can press your 8 button, and then you can press your 1 over x button, or your x to the minus 1 button. Then you press equals, but you're not quite done. You press equals so the calculator gets all that information finished. But remember, you're not, when you press equals, what you really have is this. You have 1 over RT. So after you press equals, you have to remember to press the 1 over button one more time. This is the one that will flip this guy upside down to give you the right answer. So you press that. So if you try that and you press on your calculator, let's just go through it. I'll do it with you. 2. Now on my calculator, I have to press shift in order to get my x to the minus 1 or 1 over button. You may have to press a shift in there too. It depends on the calculator. All right? And then I get plus 4 and my 1 over plus 8, 1 over equals, and then I press my 1 over one more time, and the answer that you should get after that, after you press 1 over one more time, the answer that should come out right here, your answer should come out to 1.14, right? Which is the same number that we came up with, if you go back here, for our total resistance. I'll go right back. Oh, there we just passed it. 1.14. See? We had it. So that's another way that you can do it. If you don't like common denominators and trying to work with fractions, you can use the 1 over button on your calculator, right? And this is how you would do it. So that's an option for you. Okay, so that's a series and a parallel circuit example. And so if you go to the assignment section, you will see that there's an assignment where you have a couple of circuits for you to try. See you next time.